So similar things can be applied to the phylogenetic trees, although it's a bit harder to imagine it in this case. So for the case of the three different trees, three hypotheses of the solutions, if the possibility of the particular tree is the same, it's one of the hypotheses, then the possibility of the particular tree is true will be the same. That's called a prior distribution because it's only three possibilities, one out of the three. That's if you consider they are the same. But if we given a particular data, that's our observations, a particular data matrix, then we can have a posterior probability calculations and give you an idea about what is the data and fit into the particular tree. And we'll have a different result at the end. And at the end product, we'll have something like this one. And this one has the highest posterior distribution for a particular data set. So which means that it has a higher probability for this tree to be true given the particular data set. So that's the thinking of the Bayesian inferences. But how do we do this one? Then that's the difficult part. And the posterior probability can be drawn from this inference by this Markov chain Monte Carlo process called MC method. And nowadays we also incorporate this Metropolis algorithm to use to calculate it. And Markov chain Monte Carlo method is kind of a stochastic model for keep things going. And we'll explain this a little bit over here. So we have to imagine that for any given particular topology of the tree, it has a particular distribution. So this distribution is not as simple as the thing right here. It's a bear shape. It's a complicated tree landscape, actually. So here is the topology A. There's one posterior probability among the different trees, and topology B also has different peaks as well. This is just a simplified version. So what we are going to do is trying to figure out to have a sample of the trees, and a sample of the trees are given a sum of the assumptions to reject or accept in particular case. And if it's accept, it's going to climb up to a particular highest peak over here. And if it's sometimes it will go down here and find a worse tree. And eventually we want to find a certain distribution in this particular case with the most possible, the best tree so far among the trees we got in the surrounding samplings. And how do we do that? And this is the MC process. We have to imagine the more complicated than the three taxa case we just see. So we have to start with some tree Ti, and we kind of pick up a new tree stochastically perturbing by the tree, like a NNI, the nearest neighbor interchange process, just trying to twist the tree a little bit to see if that is a better one. So we can compute the ratio of the probabilities by this one. The data part is the same as the likelihood calculations, the probability of the data of the given tree. So we can basically calculate that, and to have this acceptance ratio R. If R is larger than 1, then we'll accept the new tree, which means that this tree is better than the other one. And if R is smaller than 1, we'll have a random draw number between 0 and 1 to pick one or the other. So sometimes we'll get a better tree, sometimes we'll not. And so depend on this acceptance ratio R value to keep going on. And we'll repeat the process to number 2 and just keep doing that until we find the distribution of the tree. It's a very same thing that sometimes the tree can be trapped on the small valley or cannot move on to another area. So we need to use some method to calculate it in order to avoid this problem. And the methods right now used, for example, in Mr. Bayes, the most common use for Bayesian inferences is the metropolis coupled Markov chain Monte Carlo. It's MC. I think they just made it up. This 3MC uses the heated chain to flatten out the tree landscape. What do? Is they want to avoid this problem by that it's possible to move around the trees. And how do we do that? Of course, we can use the random starting point or the TBR methods to do so. And this method is trying to raise the power of the posterior probability to 1, and then to become a new distribution of the probability. And here is the example for that. There's the actual probability distribution of the things we are moving around with it. So for the MC process, we are kind of switch from here to here. If we are successfully using the NNI interchange problem, you can do that. I mean, the MC method, basically we want to smooth out this valley in order for them to easier to move around the tree landscape. So you can see the new distribution is a little bit different from the original one. In this thing is smooth out, so it's easier to move around the tree landscape. And this is called a hard chain because it's kind of melting the landscape into a flattened one. It's kind of strange calling. And for the ones who we are actually working on is the cold chain. That's why we call it cold chain, because it's compared to the hard chain. It's not melted. So sometimes we will have unsuccessful swap within the cold chain or hard chains. And so the best way is to have such kind of swap by some parallel chain going on all together. Sometimes if you move on to a hard chain, then you can explore the tree landscape a little bit better, and they will become the cold chain and trying to figure out what is the highest peak of the landscape. And that one will be the new cold chain. Then the other part will be the hard chain again, trying to explore the tree landscape a little bit more. So in calculations, we always, actually you can modify, it's an option in Mr. Bayes. We can doing 4 parallels at one time, and trying only one of them is cold chain, and we'll just moving on to see if we can have a best estimation of the distribution. So it's kind of hard to imagine in a way. Theoretically, you should have a lot more parallel chain going on and to have a best estimates. But people has using the simulation and other methods to say that 4 chain is already enough for this purpose. So that's why we almost always stick on 4 chains running parallel together to find a tree distribution. The idea is to see, okay, we got a tree, and we want to see what is the probability of the tree given us particular data, and what do we mean by probability of the particular tree? Then we will have to have a distribution of all the trees which can be fit by the data. So what can we get those kind of trees? That is the problem actually. So eventually we'll have a lot of samplings that can be fit into our data. And the more tree samplings we got, the better we have understanding what is the actual probability of the trees we really want in this case. So we need to have a certain burning period for this process to become an equilibrium distribution. And we'll use this diagram to explain that. So this is the generation time for, we kind of generate a population of trees every time, and to see if the data matrix can fit into that. So in the beginning, because we are starting from a random point, so the likelihood value will increase quite a lot very dramatically in the very beginning process. Once it getting to a certain period, then even if you have a lot of generation time and switch back and forth on the cold and hard chain, you'll have a very similar likelihood value for all the trees we got. And that means that all the trees can be fitting to our data matrix. So that's the population we got for the tree distribution that can fit the data matrix. So the particular tree we are interested in will be against on this tree population. So we'll have a probability over those kind of the trees we got. So this, in the beginning, that's called a burn-in process because it does not has not yet to have a very stable likelihood. So we kind of always eliminate the first portion of the Bayesian analysis and only sample probably a few generations at one time. So we can, for example, every 1,000 generation we can sample one. Then we'll have 500 trees overall, and we'll see what does the 500 tree look like. And if the 500 trees we got all support a particular branch, then the particular branch has 1.0 posterior probability. Well, I should have an outcome of the result. So for eventually we got a population of the trees. We will calculate the majority rule consensus tree among those things. And among those things with the best likelihood value, for example, if it's ABC, 90% of the tree support ABC together, then it will be 0.90 posterior probability of this particular branch right here. So if the DEF is supported by all 500 trees, then it will be 1.0. So you can imagine that since it's kind of a random selecting process, so the value will change a little bit every time you run the analysis. So today you run the analysis one time, somebody else uses the very same parameters to do the Bayesian inferences. They could obtain a different number with it. But theoretically, if the number is really large, the sampling is very good, then the number should not change a lot. It's probably 0.9 to 0.8. So that could be the differences among it. It's kind of conceptual, but we really admire the programmer. I mean, how do they actually do that? But right now we just use the program anyway. So there are a lot of things we can do to approximate the process. Again, we can use several different methods, like the NNI methods, and any kind of method you can get to have a better estimate for the distribution of the tree. It's good. But how do we do that? Geoffrey Sandstein, in his book, he stated this sentence: at the moment, the choice of a good proposal distribution involves the burning of incense, casting of chicken bones, use of magical incantations, and invoking the opinions of more prestigious colleagues. Well, in other words, there's no good proposals at all. And he's just joking, well, if you can understand his jokes. So, because it's still the same that Bayesian inferences could be also be trapped by those tree islands or be biased by a certain kind of a tree landscape. It's very difficult to speculate what is the actual tree landscape or what is the actual tree distribution. Nobody actually knows. And it also really varies among the different data matrices. And not to mention, the alignment could be totally wrong. So that's from the beginning to the end. So some people will find out, well, for the past 10 years, we have some practical examples using the Bayesian inferences. And many people found that Bayesian inferences usually will give you a higher estimation about the probabilities than the other methods, although it's not comparable in a sense. But sometimes the particular branch is very high support by the posterior probability, but will have no support or very low support for other methods, either using bootstrap or other things. Although they are kind of different concept, but sometimes it's not comparable. So people are aware of that, and we are still working on how to actually see this problem. But anyway, here are just some of the notes, and there are some prayers on the MCMC process, but actually not that many people are worried about the basic assumption anymore, because it's hard to speculate anyway. And also, if the trees has a coalescence to collect like information, or if the NNI is a good way to do so, or why you use NNI but not TBR or something else to do that. And there are some arguments, debates about it. And if you are interested, there are some information, some references you can find, but sometimes it's hard to read.